Okay.
Like his house or?
Yeah.
I got everybody unmuted, so just going to start. Hello, hope everyone's doing okay. Just a couple of quick notes. I uploaded exam number 3. It'll be ready for you, I believe, on the 25th. Yeah, on the 25th at midnight, it becomes available. You have until the 27th at 11:59. As exam number 2, this is also online, and we'll be covering chapters 10, 11, and 12. Okay. Another quick note, excuse me, concerning the new grading system. I did send an email to that effect. You don't have to make a decision right now. I'm told that you'll be given up to May the 1st to decide whether, by default, the grading system would be a P or a Z. P, you get a P if you have a class grade of A, B, and C, and if it's D or you're failing the class, it's basically a pass-fail. You also have the option to take the letter grade, and because it's a P and Z, it could affect the numbers. That depends on your program. Some programs require that you have the letter grade. If you plan to move on and professor this year, you rate many others. Most of them will accept. Some of the colleges in the program may require letter grade. Also, they may require doing financial aid. So the bottom line is how it pertains to that has for you. And if you agree, it's in my process when if you want to shoot an email, otherwise, I believe that's all I have. Do you guys have questions here today? So, no questions? All right. Well, let me proceed then. Oh yeah, don't forget I do record all these. I do record all the sessions, including the ones I do for GCC. They also, as a reminder, are on the same channel, and so you know, if you make an item, feel free to come to Tuesday. I got one session a lot. And again, I resume off the same room at Monday, Wednesday, 1 to 2, and then I'm here Saturday from noon to 5. So we got by questions, problems, and stuff. So, okay, well, let us proceed here. Let's proceed with this chapter 11. The plan here, both of the chapters 11 and 12, so we probably get pretty quick. And then I'll get this recording of it as you go and review it again. So don't forget your homework, due dates, don't forget quizzes, so if you want to do that, all the instructions, the evaluations, I don't shoot out as soon as I get the link, I will get it. Other than you can use your instructor. I don't see anything, so I appreciate the criticism. Like always room for anything. So anyway, thermodynamics. Slides are basically only 10 slides long, very short. You're given very minimal amount of information concerning this field. This field is quite big, actually. But we're going to basically talk. My phone. Okay, here we go. Collision theory. Thermodynamics, dealing with energy and the dynamics of chemical reactions and how they behave, how we can make things work as far as reaction. You know, generally, we tend to think we just put two reactants A and B together and magically you get whatever products you're going to get. That's not always the case. A lot of things have to happen before a reaction proceeds to get in there. Martin, doing good. I just read your chat. Yeah, doing okay. We're hanging in there. All this over, but it's a new kind of thing. So, collision theory. So basically, what happens is molecules they got to hit or collide together in order to react to make products. Okay, and so here in this example of the slide, we have two reactants, which look like two diatomic molecules coming together. And obviously you can see the kind of reddish orange color molecules bonded to each other, and then the blue ones are bonded to each other. They come together and they enter this phase in the center, where in this particular area, we have bond breaking, so breaking right there in this general region, and then we're forming a new bond between the two different colored molecules to eventually make two new products or whatever you're going to make. This intermediate that we have here, that I have circled right here, we call that the transition state. That is the point where the reactants, that state is, it has properties of the reactants, but it also has properties of the products. We're getting bond breakage and new formation. And that's what that transition state. Now, in order to have a successful collision, reactant bonds obviously got to break and form new bonds, as I said. Now, we can do this, but we can increase the number of successful collisions. Okay? And the way we can do that is we can just add more material. Add more reactants, reactants coming together to form the product, or we can heat up the reaction. Okay? We all know that if you're cooking something under slow cook, it's going to take a few hours for that thing to cook. But if I fire that thing, making whatever I'm making, just by using temperature. Cooking is chemical reactions, by the way. There's a whole field of chemistry called food chemistry. But nevertheless, we need more collisions, and we need more energy. Now, this particular energy has a specific name. We call that activation energy. That is the minimum amount of energy that two reactants need to become product. If the reactants don't have sufficient amount of activation energy, a collision will be unsuccessful. Nothing will happen. So we got to bypass or get enough energy to get that to react. Not only that, in the previous slide, you saw how the two reactants were orientated to each other. They have to be orientated correctly in order for bond breakage and bond formation to occur. So orientation is a factor, energy is a factor, and the number of collisions that occur is a factor. Oops, sorry about that. Let's get back down. Okay. So we can increase this rate of reaction. This reaction of two reactants. There's a rate involved with that. That's how fast things are occurring. Now, one thing to increase the rate is to increase the reactants, add more, increase the concentration. Okay, and that's what that reactant in the bracket means right here. Remember the brackets, we introduced that a little bit in acids and bases when we were talking about pH concentration. The brackets around reactant is telling you the concentration. So increase the concentration of reactants, hence we get more collisions. Okay, let me back it up. We increase the temperature. Okay, by increasing the temperature, we get molecules to move faster. Stands to reason. Okay, we get them to move faster, more collisions, and plus we're giving energy into the system so they can overcome that energy of activation, have sufficient energy to become product. Okay? So another thing we can add what is sending forward in the lack of a lot of acid exhaust. Okay, so catalysts are around your body. You call those enzymes. Reactions in your body will occur by themselves without these enzymes. Otherwise, they would occur in weeks for a reaction. So catalyst very important. Okay, so again, the activation is an energy to turn reactive fast. Okay. With respect to equilibrium reaction, we kind of introduced it a little bit when we're talking about the acid. And in chapter, we talked about how some has weak acids, and therefore in that 11 carrier dissociate, and that good zero is what we call the process when they react. That means that the reaction of ACD equals the reaction of CD and AD. We process is equal. We call that interaction. Yeah, that's the reaction. Most ones are things that are the same thing. Acidification and equilibrium. That I'm going to follow next. I will go to that. But basically, that is not a reaction where the axis is how the axis is horizontal axis, and the vertical axis is energy. Energy starts at zero. The reaction starts at zero in the left corner. And then as it proceeds, it goes up, and then the reaction sees different stages. This plot that we need the transition state. The first slide I showed where you have the reactants are breaking the bonds and forming bonds. That is denoted on that graph on the very top of the hill by the letters TS, transition state. Okay. Now, the HLH is the change of energy. Is a change, also called the reaction. What is the change of energy? That is represented in the graph. There is a difference in energy between the products on the right side minus the energy of the reactants. Where the reaction would tell us what this reaction is. The exothermic reaction by exothermic, meaning that it gives off heat and gets hot. An endothermic reaction, meaning it gets heat and gets into the environment and actually gets cold to the So delta H is the change of heat energy, the change of reaction energy. Okay, and that's the product heat. Now, I just introduced endothermic. The term endothermic. In this scenario, reactants gain or absorb the environment. And what is the reaction? It's cold. But the main is that heat or energy is a reaction. Okay? And hence it's an endothermic process. It's heat from the earth. An exothermic heat is a product. And therefore, you feel that reaction when you touch it. It gives off heat because heat is a product and it gets warm. A classic example of these two processes is buying at the pharmacy a cold pack or a hot pack. If you buy a cold pack and you smack the bag, you feel it get cold, and that's where you put it on your muscles, when they're aching and so forth. Okay, you can also buy a heat pack where again there's two reactants in there. Smack the bag, break it up, and that little packet gets warm. That's an exothermic reaction. The cold one is an endothermic reaction. Okay, now we got a little bit better view of that graph. Okay, now, as I was saying, the axis here is an energy on the vertical one. We got energy, and we could arbitrarily put numbers up to this. It's a scale. We got a scale down here, and that's basically this axis just tells you how the reactance is proceeding as it goes through this process. But over here, we could put energy values to maybe see this a little bit better. So we can say 10, 20, 30, go up the road. That's our energy. Right now, they're arbitrary units. It's energy units. Okay. Now, if you notice where the reactants start off, okay, if we draw a line across to see the energy, we could arbitrarily say, okay, depending on the axis we just created, this thing starts off with about 20 units of energy. Okay. And if we do the same thing with the products, where the products ended up, we could say, okay, this thing ended up with about 10 units of energy. Delta H is the change of energy between the products and reactants. Simply means that if we take 10 minus 20, we end up with a negative value, negative 10 energy units. That negative tells us it's exothermic, okay? Exothermic reaction. That's for delta H. Now, if we look at the energy of activation, that's where the reactants begin. Let's say that's 20 again. And then we look on top of the hill. Okay? We draw a dotted line over to the axis. This could be, I don't know, 10, 20, 30, 40, say 50. Okay? That energy of activation is the difference between 50 and 20. So it takes about 30 units of energy in this example right here for this reaction to proceed. to have at the minimum 30 units of energy to reach a transition state up to here. Okay. Once the reaction proceeds, then the reaction drops over the hill and ends up to the final energy level of 10 units. Okay. So we have the energy of activation sitting there, the transition state on top of the hill. The reactants here in this example begin at 20 and end up with 10 units of energy, which means that delta H has a negative value because 10 minus 20 is a negative value. So in this example, delta H is negative, hence it's an exothermic reaction. Okay. Now the difference between an endothermic is the products, and we have some examples of that, the products may end up maybe up here. Okay. And if we go through the same scenario, the products are a higher energy level than the reactants. So if we subtract the products, we can say, let's say this is like 30 units of energy. Okay, so 30 minus 10, we get, 30 minus 20, because that's where the reactants began, we have positive 10. Okay, positive 10 delta H, which means it would be an endothermic reaction. Okay, but you can go mathematically through the exercise where you can see that the products are in much lower energy level than the reactants when they began. That indicates exothermic reaction. Okay, so and this is an example of endothermic. You can notice that the products, you can see that the product's energy level relative to the reactant's energy level ends up at a higher energy level, the products that is, than the reactants. And if we subtract products minus reactants, we end up with a positive number, hence endothermic. Okay. And so here, we're asking to label the transition state, which is already labeled for you. The energy of activation, okay. Delta H for this endothermic reaction is labeled for you, and that's the difference of the energy level between products and reactants. And then label where the products and reactants are, okay. So you should be able to look at one of these graphs and then determine whether it's endothermic or exothermic, and also be able to label these 5 points on the graph: transition state, delta H, reactants, products, and energy of activation. Okay. Looking at this, they're asking you here, is delta H positive or negative? You can go through that exercise we just did by putting numbers in there, or you can just see that the products is at a higher the product's final energy level is much higher than the reactants. And so in subtracting those numbers, I end up with a positive number. So this is an endothermic reaction. Hence, it will get cold because it's taking energy from the environment. Here are both of the graphs shown side by side. I mean, you can see the difference of where the products are with respect to energy level, the final energy level. For exothermic, it's on top. The endothermic reaction is on the bottom. Okay, so the only difference between these two graphs is where the products end up with respect to energy. Okay, all right, that's the only difference. Other than that, they all have the same similar energy of activation, reactants, and delta H. Okay, with respect to a catalyst and the energy profile, as I mentioned earlier, a catalyst actually helps or assists a reaction to proceed. It doesn't get involved with the reaction directly. It does not become part of the products. All they do is lower the energy of activation. Okay, and you can see here that this is with a catalyst. Normally, without a catalyst, that reaction requires a lot more energy to become product. And that's all a catalyst does. It reduces the energy of activation of a reaction. Okay. That, come on. Tell you what, chapter 11 is done. Okay. So what to take away from this particular chapter is just look at the energy profiles that we talked about, the graphs. Be able to identify the different positions in the graph, transition state, where the products are, where the reactants are, where's delta H, the reaction or the heat of the reaction. Be able to label them or determine from a graph where they're at, and the energy of activation, of course. And then also from the graph, be able to determine, is this an exothermic or an endothermic reaction? Okay. All right. Any questions? Very short chapter. Okay. Let me load up number 12. I don't know if it's my connection or it's my cell phone or just the internet in general, because there's a lot of traffic going on the internet. So, okay. Any questions so far? All right. Note this one. This is 18 pages too. Very short, but very important chapter, because it introduces the concept of the mole. Okay, which sometimes can be kind of challenging to grasp, but it shouldn't be, because, for example, if I tell you I have a dozen donuts, which what I did, by the way, I do have a dozen donuts. The point is, that a dozen equals 12. Okay, so we understand that part. And I want you to take that concept about the dozen and apply it to the mole, because the mole is nothing more than a number. It just happens to be a very big number, much bigger than 12. And it's specifically 6.02 times 10 to the 23rd. Okay, so in this particular chapter, if you remember, we talked about, we worked scientific notation. So you may want to refresh your memory on how to do scientific notation calculations on your calculator. If you recall, you either had a double E button or EXP button, and the newest ones had a different button where it was the times 10 to the X power. Okay, so you refresh your memory on how to utilize your scientific notation, and also refresh your memory on significant figures. There, you thought we were done with sig figs, right? No. Sig figs stay throughout science. Okay, so refresh your memory on that and so forth. Now, with respect to the mole, this is also known as Avogadro's number. There's a picture of the scientist on the right side. I mentioned that you're familiar with dozen. Obviously, we all are. That's a number. However, a mole, its number is big. It's number 0.02 and move it to the right 3 times. Notice how big that number is. In fact, that number is so big that if you were to count that number, starting with 1, and just count 1 number per second, it literally would take you thousands of years to get to the end of that number. Okay, and that number is a constant. So here's your first conversion factor given to you. 1 mole is equal to 6.02 times 10 to the 23rd. Now, you remember that chapter we did on conversion units from one metric to English and so forth? And I emphasize the fact that using that dimensional analysis, we're keeping track of the units. Well, this is where you need it because we'll be using it quite a bit. Now, any ratio, and also emphasize that, any ratio that you have, be it dollars per hour, be it miles per hour, I can write one or two ways. I can put, in this example here, I could put Avogadro's number on top of it as a numerator and 1 mole as a denominator, and vice versa. And which one I use to do my mathematics depends on the question. So these problems that we're going to be doing for this particular chapter, it's a matter of setting your problems up correctly and follow the units and making sure units cancel out. And then what's left is basically you doing the math on your calculator, okay? So, all right. Now on the periodic table, we had the atomic weights, right, sitting there right below the symbol of the atom. And that number is the atomic weight of that particular element. But all those atomic weights have units. The units of the atomic weight are grams per milliliter. Excuse me, grams per mole. I was thinking of density here. That's further down the road. Grams per mole. So if you look at the periodic table and you look up carbon, you see that its atomic weight is 12.01 grams, and this should be per mole. Okay, grams per mole. Hope you can read my writing there. Fingers a little bit too big. Okay, so think about that for a second. If you weigh out 12.01 grams of carbon, you have 1 mole. And if I have 1 mole, I have 6.02 times 10 to the 23rd atoms of carbon. Okay. Sodium, also looking at the atomic weight, has an atomic weight of 22.99 grams per mole. Same scenario. I weigh out 22.99 grams of sodium metal. I have 1 mole, and I have 6.02 times 10 to the 23rd atoms of sodium. Okay. Now, obviously, sodium is a lot bigger than carbon, hence the higher molecular weight or atomic weight. Okay, almost twice that. And it makes sense if you think about it. You know, if I got a dozen small eggs, I got 12, right? If I got a dozen large eggs, I have 12. However, we know that the small eggs weigh much less than the large eggs. Okay, so the same principles applying here, except the mole is our dozen, and our mole tends to be a very big number. Okay. All right. So let's proceed. Now, the mole is basically that number 6.0, Avogadro's number, 6.02 times 10 to the 23rd entities. It could be anything. It could be atoms, it could be ions, it could be molecules, it could be formula units like sodium chloride there and aluminum oxide and so forth. It could be bananas, it could be oranges, it could be anything, okay? It's just a number to tell you how much of whatever you have, okay? So, come on. Oh, my cell phone's stuck. There we go. So, if we look at the periodic table and like we just did carbon. You see that carbon has 12.01 grams per mole. Gold is 196.97 grams per mole. And sodium, obviously, again, 22.99 grams per mole. All of them have, if you weigh that amount out, have 6.02 times 10 to the 23rd atoms of each of the elements there. Okay. And that's analogous to, I got a dozen small eggs, a dozen medium eggs, and a dozen large eggs. Okay. In each case, I got 12, excuse me. In each case, I got 12 of the eggs, but each one was different because. So, yeah, the other concept that we need to introduce, so we're going to use this quite a bit, okay, and that's called the molar mass, all right? Now, in this scenario here, they're saying, they're asking you to calculate the molar mass of barium hydroxide. Now, the molar mass is simply put is the atomic weight of all of the atoms, all of the elements that are used for that particular compound, okay? And we add them up, and we have the molar mass. But before we can figure that out, we have to figure out the formula for what we're being asked to do here. And this is where the previous chapters, we emphasize the fact about the ions and the polyatomic ions. So it's coming into play here. We're trying to put all that together, okay? And the nomenclature where we're trying to name the compounds and then from the name give the formula, well, here we are, okay? It says calculate the molar mass of barium hydroxide. Okay, now before you put anything down, my suggestion is first put everything in ionic form, okay? Because this is an ionic compound. Hydroxide, look at the polyatomic ion table on the periodic table, okay? You will find hydroxide. Also, hydroxide was introduced in the acid-base chapter, where the hydroxide was defined as an Arrhenius base, okay? So first write the ions first before you put the molecule together. And we look up barium on the periodic table to refresh your memory. Barium is on group 2. It has 2 valence electrons, point 1. Point 2, it's a metal, okay? And all metals lose electrons. Barium is going to lose those 2 valence electrons and end up with a positive 2 charge. So write down, let's do this. Barium, the +2. The barium ion is Ba +2, okay? The hydroxide ion, just by the name, should send you to the polyatomic ion table of the periodic table. And you see that it's OH with negative, okay? That's a packet. Remember, the polyatomic ion, we don't separate these, it's a packet. Now we have to put them together to write the formula. Well, when we write the formula, recall, we got to put enough negatives with enough positives to cancel each other out. Barium has a +2, hydroxide has a -2. That tells me that I need 2 hydroxide ions to cancel the +2 of the barium. And since this is a polyatomic ion, I need parentheses to demonstrate that I need two of them. Therefore, that is my formula, okay? Barium hydroxide, it's an ionic compound. Now, at this point, we count the number of atoms that we have in the formula we just wrote. We have 1 barium, okay? There's 2 oxygens and 2 hydrogens. We look up the atomic weights for each of the elements and we sum everything up. So you can see barium, its atomic weight, and when you're finding atomic weights, do use the periodic table that we have, okay? You'll find if you Google periodic tables, you're going to get an infinite number of periodic tables and atomic weight numbers. So, but to keep your numbers straight with respect to the answers you will find in exams and quizzes, whenever you need to use atomic weights, use the atomic weights from our periodic table. So in there, you'll see that barium has an atomic weight of 137.33. Oxygen has an atomic weight of 16, and there's 2 of them, hence that 2 times 16. Plus, oxygen has an atomic weight of 1.01 for each one, but there's 2 of them. So once you add everything up, you'll see that the molar mass for barium hydroxide is 171.35 grams per mole. Okay, so meaning that If you weigh out 171.35 grams of barium hydroxide, you have 1 mole. And in having 1 mole, you have 6.01 times 10 to the 23rd molecules of barium hydroxide. All right, and not 0.102, sorry. Okay, so in calculations with respect to Avogadro's number, I mentioned to you earlier in the first slide that Avogadro's number is a ratio. So being a ratio, we can set it up one or two ways, which is given up there in the left corner and in the right, okay? With Avogadro's number in the numerator or in the denominator. Which one we use depends on the question and how we follow our units. So question number 1 asks, how many calcium atoms are in 0.25 moles of calcium? Okay. How many calcium atoms are in 0.25 moles of calcium? All right. What we're looking for is calcium atoms. Okay. Therefore, that suggests that we're going to take that 0.25 moles of calcium and multiply it by Avogadro's number and use the left factor. Okay. And that's what we do. Note, keep track of your units. Note that the moles cancel, leaving us atoms in the numerator. Now you bring in your scientific notation calculator, you type in 6.02 times 10 to the 23rd, multiply that by 0.25, and you have, as your answer, 1.51 times 10 to the 23 calcium atoms, okay? Second question is asking you calculate the moles of 3.75 times 10 to the 27 molecules of oxygen gas. Okay, so what are we looking for? We're looking for moles as our final answer. Therefore, we're going to be using Avogadro's number, but we're going to use it set up like that. Okay, because again, by keeping track of the units, that lettering MLCLS, that's shorthand for molecules. Molecules cancel, okay, leaving us with moles. And so if you were to actually have 3.75 times 10 to the 27 molecules of oxygen gas, okay, you will have 6,230 moles of oxygen gas. Notice something too that you want to be aware of. The word problem talked about oxygen gas. Refresh your memory about the gases that are diatomic. One of them is oxygen. You remember, have no fear of ice cold beverage. Therefore, we're talking about O2, okay, not oxygen. If that would have asked for oxygen atoms, then obviously it is O by itself. We're talking about oxygen gas. Okay. Now, excuse me. In these questions, they're asking you to convert grams to moles. Okay. We'll find later on that we really, if we're in the lab doing something and we need X number of moles of something, well, we don't have a balance that measures moles. So we have to convert to grams, okay? And in fact, you're going to find that this concept of the mole is very important because the only way we can get from grams of A to grams of B is through moles. So that's important that we grasp how we can convert grams to moles and moles back to grams, okay? Because moles is the intermediate. Okay, so here, and recall that the atomic weights of the elements and or the compounds have the units of grams per mole. And therefore, the atomic weights or the molar mass is another ratio that we can adjust accordingly. First question says, how many grams is 1.667 moles of oxygen gas? And so they're giving you the moles of oxygen, okay? And you're looking for grams. Now, we have, what we need here is the molar mass of oxygen gas, okay? Because the molar mass has a units of grams per moles. And then you have to recognize that they're saying oxygen gas, so we're talking about O2. So the molar mass of oxygen gas would be 32 grams per mole, okay? And then with that information, we can multiply the number of moles we have by the molar mass of oxygen, and we end up with grams. I'll show you that in a second, okay? Second question, they're asking you again, this time they're saying how many moles, that in mind, our final answer should be in moles, is 45 grams of silver, okay? Here, silver, we're talking about the element, so we gotta go to the atomic weight and find that from the periodic table. So we need the atomic weight of silver to be able to answer this question, all right? Third question, they give you the number of moles of water, okay? And they're asking you to determine how many grams that is. And they're talking about water. Well, I need to determine the molar mass of water, which means I need to know the formula of water. And the formula of water, which we all know, H2O, okay? Okay, so H2O meaning one oxygen, two hydrogens, we add that up, 18.02 grams per mole, okay? Finally, the last one is a little more challenging, but it's okay because we're just going to add another factor. They're saying how many grams is 4.75 times 10 to the 16 atoms of potassium? Well, two factors here. One, Avogadro's number, which takes us from atoms of potassium to moles. Now that we know the moles of potassium, we need the atomic weight of potassium to give us grams. So we're going to need two factors there to be able to answer that question. All right, let's work through it. This is how it's set up. So if you look at the first one, they gave you the number of moles of oxygen, and they want to know how many grams that of oxygen that corresponds to. Okay, so this is the number of moles of oxygen. This is the molar mass of oxygen, two oxygens, each one 16, so that's 32 grams per mole. Look at my units. Moles cancel, leaving me grams. Let me get a smaller pen here. Okay. You notice that the moles cancel out, leaving us with grams. Second question, they gave us 45 grams of silver. We need the atomic weight of silver. We get that from the periodic table, okay, which has the units of grams per mole. Since we're starting off with grams, we're going to divide by the atomic weight, or set it up with the atomic weight being the grams being the denominator. So our grams cancel, giving us with moles as units. So that corresponds to 0.42. Now keep in mind the sig figs, okay? You got to follow them through. You're given 4 in the first question, your answer should end up with 4. Now, the atomic weights, the atomic weights or molar mass, don't use those to determine sig figs. Those original numbers came from whole numbers, and you have an infinite number of sig figs. So you don't use atomic weights and molar mass to determine your sig figs. Okay, the third one, they gave you the number of moles of oxygen, and we need to figure out the molar mass of, water. Okay, well, to do that, we need the formula, H2O, and its molar mass is 18.02 grams per mole. Yeah, grams per mole. Hey, think about that for a second. The molar mass of water, 18.0 grams per mole. If you go to your kitchen sink and you weigh out 18.0 grams of water, you have 1 mole, 6.02 times 10 to the 23rd molecules of water. Now, think about all the water on Earth. Can you imagine how many molecules of water there are on Earth? That's mind-boggling. The number's humongous. And that's just water. Okay. Finally, the last part, let me erase a little bit of this so get a little clearer. I'm asking you how many grams are in 4.75 times 10 to the 16th atoms. Well, we need 2 factors here. The first factor is Avogadro's relationship with 6.02 times 10 to the 23rd units or atoms in the denominator. Okay. Then we need the second factor, which is the atomic weight of potassium. Okay. And we get that from the periodic table, 39.1 grams. Follow your units through, we end up with grams. Okay. Imagine for a second, look at that big number you have of the number of atoms of potassium. That's a big number. But their weight is 10 to the negative, in the magnitude of 10 to the negative 6 grams. That's extremely tiny. We don't have, there are balances that can weigh like that, but not very accurately. So that's a small amount for having such a large number of atoms. Okay. So here's some examples of converting from grams to moles. Eventually, we're going to get to the point where we go from grams to moles and back from moles to grams, okay, depending on what we need. Okay, now let's talk about, we just introduced molar mass, okay? I want to introduce molar volume, okay? And that pertains only for gases. And specifically, it only pertains to situations that we call STP, standard temperature and pressure, okay? The standard temperature is 0 degrees Celsius, and the standard pressure is 1 atmosphere of pressure, okay? So 0 degrees Celsius. Under those conditions, and only under those conditions, and only for gases, there's a whole new relationship for you. And that relationship is that under those conditions, any gas occupies a volume of 22.4 liters. Every mole of gas occupies a volume of 22.4 liters per mole, okay? In this example, we have a number of gases. We have 1 mole of each. Obviously, they all have the same number of molecules. They're all going to differ in molar mass because there's different weights, okay? But the thing they all have in common is that at 0 degrees, and I emphasize the fact, at 0 degrees and 1 atmosphere pressure, those gases occupy a volume of 20.4 liters. If the temperature is different or a different pressure, then this does not apply, okay? Molar volume. So this is the conditions right here. 0 degrees Celsius and 1 atmosphere of pressure. And the other aspect, you got to remember that we're dealing with gases only. So you may want to refresh your memory about the elements that are gases. We had a slide back, I forget what chapter off the top of my head, but it could have been the periodic table chapter. We talked about which elements were solids, which were liquids, and which were gases. All right, so how do we use that relationship? Like any other ratio, okay? Any other ratio that I keep emphasizing, it can be written one or two ways, like that. And depending on what the question is and what we're looking for, that's the one we use to do the mathematics. Now, I know you might be tempted to use this other system. I've seen it before where you do a ratio here and then do it again at different times. I want to suggest using that method because we're going to find down the road that we're going to set up conversion factors like this, where you're going to have at least at the minimum 4 and sometimes maybe even 5. And by keeping track of your units, you'll be able to get things to cancel, and that will tell you that you had it set up properly and you set it up, no question. Okay, so I would not recommend using another alternative method of going from one unit to another unit to a third unit to a fourth. Okay, so here they're asking you, what is the volume of 1.25 moles of argon gas at STP? The key part is STP. They may say STP, they may say 0 degrees in 1 atmosphere. That is STP. That being the case, I can use this one of these relationships up here, okay? And since we're asking for the volume, given the moles, then we need to use the one on the left, okay? Okay, because our units follow the units, moles cancel, leaving us with liters. The rest is a matter of doing the math. And so 1.25 moles of argon gas at STP occupies a volume of 28 liters. Okay. Second question, how many moles is 3.4 liters of oxygen gas at STP? We're looking for moles. We're given liters. Okay, so it looks like we're using the one on the right. Okay. And sure enough, okay, check, follow the units. My liters cancel out, leaving me units of moles. Now it's a matter of doing the math. 30.4 divided by 22.4 gives us 1.36 moles of gas. Now think about this for a moment. Does that answer make sense given the information you have? Well, it does, because if you think if you have 1 mole of gas, it only occupies 22.4 liters. The fact that you're told that there are 30.4 liters is much greater than 22.4, so I would expect a number much greater than 1, in this case 1.36. So the answer makes sense with respect to how you set that up. Okay. And finally, jumped ahead, sorry. What is a mass? Well, as I said earlier, they're asking for mass, so we got to get an answer in grams, but we're given 4.5 liters of chlorine gas. Well, since we're still at STP, we use the first conversion factor to get us some volume to moles. Okay, so you can see liters cancel out here. Once we know that, we're in moles of chlorine gas, but we're asked to go to mass. We need that answer in grams. Well, then we need to find the molar mass of chlorine gas. Okay, key word chlorine gas. Okay, not the chlorine atom. Chlorine is one of the diatomic molecules, so that's Cl2. So it's 35 times 2, so we end up with 70, what's 35.4 something. So we end up with a molar mass of 70.90 grams per mole, okay? Following through, our moles cancel out, leaving us the units of grams. Now you just do the math, and you should get an answer of 14.2 grams. So 4.5 liters of gas, okay, at STP would weigh 14.2 grams. All right. Any questions so far? Feel free to jump in there since there's only 2 of you. All right. This here this flow chart summarizes this whole process, okay? Further down the road, we're going to have another flow chart to kind of help you out to get from point A to point B. Note what we got here. The intermediate is moles. You can't get through you cannot go directly from grams to atoms. Cannot. You cannot go directly. The same is true, you can't go directly like this. So I'm saying no like that. Or I can't go directly from grams to volume, okay, without going through moles. You've got to go through moles. All right, so let me clear the mess up here a little bit. So if you have grams and you want to get to moles, you need the molar mass or the atomic weight if it's an atom, it's an element, okay? Remember, they have units in grams per mole. Having that information gets you to moles, okay? From here, if you are at STP, and again, only at STP, you use this relationship of 22.4 liters per mole to get you to volume, okay? Or you might be at moles and you want to know how many atoms you have, well, you use Avogadro's relationship, Avogadro's number, to get you to atoms, okay? So you can go from atoms to moles to volume, or you can go from grams to moles to volume, or grams to moles to volume, okay? Or vice versa. It looks like a big mess there. But everybody has to go through moles in order to get from point A to point B. So this flow chart really summarizes the calculations here. And you're going to have another one further down the road when we start looking at chemical reactions, where we will look at A plus B to give me C. And if you start off with X number of grams of A, how much C can you make? Well, that's going to be dependent on getting the A to moles, and then looking at the balanced chemical reaction. We talked about balancing and get us to moles of whatever product we're looking for. Okay. All right. So, an example: how many grams does the 17.35 liters of neon gas mass at STP? Okay. So they're asking you here, what is the weight of 17.35 liters of neon gas at STP? Okay. Well, and then the second part is, well, how many atoms does this correspond to? All right. So we write down what we have. And I even gave you the answer here for right now. We know we're given 17.35 and we're trying to get 2 grams, 17.35 liters, and we're trying to get grams of neon. Okay, so I need my conversion factors here, where one, since I'm at STP, I can use 22.4 liter per mole relationship to get me 2 moles of neon gas. Then Once I'm there, I'm at moles, I need to get the grams, so I'm going to multiply by the atomic weight of neon, which we get from the periodic table. Notice that our units cancel along the way. And if you set this up properly, boom, you know that my final units are in grams, and the rest is a matter of just doing the mathematics. And you should end up with 15.6 grams. And note the significant figures here. We got 4 sig figs and 3 sig figs as an answer. You might ask, well, why is that? Okay, I told you that we don't use the atomic weights or the molar mass because they were originally whole numbers in the infinite number. But the 22.4 is not an exact number, it's a measurement. Okay, so therefore, being a measurement, it will be a factor with respect to sig figs. And it has 3 sig figs, so our answer should have 3 sig figs, even though we began with 4 sig figs over here at 17.25. All right. Second part of the question, they want to know how many atoms does this correspond to? Well, obviously, we're given 17.35. I want to get to atoms of neon. Okay. Here again, I need 2 factors. First one is we're at STP, that gets me into moles. And then I use Avogadro's number because that gets me into atoms. And again, looking at the units, my liters cancel, my moles cancel, leaving me with atoms. So that's been properly set up. Okay. All right. We got a few more slides and we're almost done with this chapter. Okay. Now, we did briefly talk about density in the lab, which, by the way, a side note, I did upload 3 labs for you, so you might go up there and take a look at them. Basically, they look at a video and then answer some questions from the video. Okay, so in density by definition is simply another ratio. How about that? Which happens to be the mass over volume. Okay, so everything, every piece of matter on Earth, anywhere has volume. So if we get the weight of it and we get its volume, we have one of its physical properties would be density. Okay. Now we can use the concept of molar mass and molar volume to figure out the density of a gas at STP. And so here they're asking to calculate the density of ammonia gas at STP. Okay. Well, we set it up as follows. We need the molar mass of ammonia. 1 nitrogen, 3 hydrogens. That corresponds to a molar mass of 17.04 grams per mole. We know we are at STP, and so that relationship is true, 22.4 liters per mole. If you look at the units, you'll see that when you do that, you're dividing the molar mass divided by the molar volume. Moles cancel out, leaving you with the units of grams per liter, okay, which is density. So in this particular case, just knowing the molar mass of whatever gas you're given divided by 22.4 liters would then give you the units of grams per liter, okay? Be careful, sometimes they give you questions like grams per milliliter, which wouldn't be correct, right? Because look at the units you're starting off with, liters, or they may just say grams. Well, that's not density. Density is a ratio of mass over volume. Okay, so in this example, ammonia has a density of 0.761 grams per liter. And guess what? What does that mean? Okay, let me back up here. What does that mean? Think about the answer here. 0.761 grams per liter. So if I had 1 liter of ammonia gas, it's only going to weigh 0.761 grams. It's pretty small. Be very light. All right. Percent composition. Every compound molecule has well, I should say molecule. Every compound has a percent composition. All that is the atomic weights of all the atoms involved in the molecule divided by the molar mass of the molecule. For example, water, we mentioned that earlier. Water has a molar mass of 18.2 grams per mole, okay? In water, there's 2 hydrogens. So each hydrogen brings in 2.02 grams of hydrogen. Divide that by the molar mass times 100, it constitutes 11.2%. Hydrogen constitutes 11.2% in water, H2O. You do the same thing for the oxygen. Oxygen has 16 grams. There's only 1 oxygen divided by 18.02 times 100. Oxygen represents 88.79%. These numbers should add up to 100%. Okay, that is a constant, regardless of where you find the water. Water here in Arizona is 11.2% hydrogen and 88.79% oxygen. Water out in space, same material. Okay, same percent. With that being said, once you be able, if you're given the formula, you can determine the percent composition of all the elements. For example, this problem here. This is, they're asking you to find the the percent composition for TNT, otherwise known as dynamite. This is trinitro-toluene. Trinitro-toluene. And they give you the formula here, okay? There's 7 carbons, 5 hydrogens. In parentheses, you have nitrite group, NO2. There's 3 of them, which means you have 3 nitrogens and 6 oxygens. Okay. This, by the way, was discovered by Nobel. That's how he got so much money, by Nobel Prize. The prizes that are given each year for science and medicine and so forth. All that money came from dynamite. Okay, if we do all that, what happens is the molar mass or TNT is 227.15 grams per mole. When we run through the composition, we had 7 carbons, 5 hydrogens, 3 nitrogens, and 6 oxygens divided by the molar mass. We end up with the percent composition of each element, which, if we add up, should add up to 100%. So that's a check for you if you do a calculation. If your numbers don't add up to 100% somewhere, someplace, you may have done a mathematical error. Okay, so carbon of TNT consists of 37% carbon, about 2%, a little bit over 2% hydrogen, about 18.5 nitrogen, and almost 42% oxygen. Okay. In the chemical world out there, we do this a lot. When I would make a new compound, clean it up, purify it, I would then send it out for analysis and ask them to give me carbon, nitrogen, oxygen, sulfur, whatever I wanted. Then you take the percentage that they sent you and you back calculate, and you can come up with a general formula of the compound that you make. All right, let's clean that up. Now, try this at home. Okay, try these problems at home and see if you can come up with the answers here. The question is, how many liters is 3.425 grams of carbon dioxide occupy at STP? You should come up with 1.74 liters. Okay. Second question asks, how many molecules are in 3.425 grams of carbon dioxide? You should come up with 4.68 times 10 to the 22nd. Okay. And then the last question is, how many grams will 3.0 times 10 to the 15 molecules of carbon dioxide mass? How much does it weigh? You should come up with 2.2 times 10 to the negative 7 grams. So try these at home, working through. If don't get those answers, then shoot me an email and I'll try to talk you through it through email, or I have office hours Monday and Wednesday 1 to 2 here on Zoom, and Saturday 12 to 2 here on Zoom. Other than that, congratulations. You just went through 2 chapters. Okay, very short chapters. Now, the next 2 chapters, 13 and 14, they're a little bit longer. Okay, there's a little bit more involved with them, so it'd be, from your perspective, if you would go and view on the website the videos pertaining to those chapters, and then when I come talk about them, I think the information would be hopefully not so foreign, okay, and maybe more understandable. And then also by viewing those videos beforehand, you can make note of some questions, and then when we come and talk about it here, you can throw a question through the chat or unmute yourself. In fact, if you like, you should be all unmuted. So other than that, I think we're good for today. In fact, I got a little bit early. Does anybody have any questions? No? Morgan? Jason? No? Okay. Well, you guys, if you do, I'll hang out here for another 10, 15 more minutes. Other than that, I got to close it so I can get the recording going. Let me stop the recording.